Have you ever trained a machine learning model that performs brilliantly on training data but crashes on new data? That is not bad luck. That is called overfitting, and that happens with everyone. And if your model is too simple to learn the real pattern, that is called underfitting. So now here is the twist. There is a mathematical technique that keeps your model perfectly balanced between these two extremes, underfitting and overfitting. That technique is called regularization. And once you understand it, you will never look at overfitting the same way again. So hey everyone, I'm Akash Gupta, and here on Concepts of AI, I simplify complex AI and ML concepts so you can actually feel what is happening inside the math. So there are two types of regularization, L1 and L2. So today we will break down L1 and L2 regularization, why they work, how they differ, and how they literally reshape your loss function. Let us just do a brief introduction about the underfitting and overfitting. So let us visual refresher. So you can see on the screen a simple model like a straight line trying to fit the curved data that misses the real pattern. That is called underfitting. Then next graph is a complex model that bends and twists to fit every noise point, that memorizes everything but learns nothing. That is called overfitting. Now our goal is that sweet spot where the model learns the real pattern but ignores the noise. Now, so how do we stop a model from memorizing noise? We simply punish complexity using regularization methods. So regularization does exactly that. It adds a penalty term to the loss function for large weights. Like you can look at the screen now.
So on the screen we have L1 and L2 regularization both. Here the L1 is called Lasso Regularization and L2 is called Ridge Regularization. Okay, now here we have the formulas for loss functions in both cases. So for L1 we have the loss function is error. Error is nothing but the normal error or we have been doing right in the machine learning algorithms. Like for linear regression it is mean square error. For logistic regression it is cross entropy loss. So this is the same error. Okay, now to this error we are adding another penalty term. Okay, that is nothing but a lambda into, now in case of L1 we are multiplying the lambda with the summation of the absolute value of weights. Okay, and here this lambda is called the strength of the penalty. We will talk about lambda later in the video. So here this is the loss function we have, that is error plus lambda into summation of absolute values of weights. Now again we want to minimize this loss. Okay, similarly for the L2 we will add lambda into summation of the squares of the weights. Okay, so now we have to minimize this loss, so we will differentiate this loss function here. So for the L1 if we do it, so that will be nothing but the del L over del W is equal to del
E over del W, that is the error derivative, that is normal thing, plus lambda, that is constant. Now when you differentiate the absolute values of weights like this is the summation of absolute values of weights. If you differentiate them, you will get 1 or minus 1, right? Because absolute value of W1, it could be plus W or minus W. So if you differentiate that, you will get either plus 1 or minus 1. So here you will get either plus lambda or minus lambda. Similarly, for another type of regularization, that is called L2 Ridge regularization. Here again you add lambda into summation of W squares of weights, and when you differentiate it, here you get 2W. Okay, so that is using power rule. When you differentiate W square with respect to W, you get 2W. Fine. So this is what we have. Now let us see how does it work. So when we try to minimize the loss, we try to minimize both error and this penalty thing. Okay, now let us look at this graph. Now suppose for example if I talk about L1. So here basically this is your loss or the error contour. Okay, what does it mean? Means this is your actual minimum. Means if I don't do regularization, then my actual minimum of the loss is here, which we have been finding right in our algorithms. But once I add regularization, now what is this? This is nothing but the graph or the curve for the penalty thing. So for L1 norm or annual penalty, it is lambda into summation of absolute values of weights. So this is what we get. Okay, so here it is nothing but the small rectangles. Okay, and as I basically increase the lambda here, the strength of the regularization, the curves or these rectangles get smaller, right? Now, so I have the rectangular shape for the L1 regularization, that is called lasso. Now, if I need to minimize both, so I need to get the intersection point as my optimal point. So actually this was the minima, but since now I need to take care of this rectangular shape also, or this penalty also, I will try to increase the loss a bit. So I will start from actual minima of the loss, and then these are the ellipses belonging to a single value of loss. So here the loss could be L, small l1. So this whole curve is for small l1, this whole curve is for small l2. I have increased the loss even a bit. Then if I increase the loss further, then I get a contour for L3. So all these ellipses, one ellipse belong to one error value, right? So I will keep expanding it unless I reach this penalty curve. Okay, so at this point, both curves are getting satisfied, right? I am getting an error from the ellipse, which is your first error term, okay, and that error is lying on the penalty term curve as well. So this is right. Now if I won't expand further because that's not of any use. Okay, this point is satisfying both terms in the loss function, and if I expand further, my loss will increase further. I don't want that. Okay, I was just expanding in order to meet the penalty curve, and I have got it. So this is the intersection point, and that's where I will stop. Now the thing is, here you will stop at the point where one of the w's might be 0 or it will be 0. Okay, how? Because when you differentiate here, you will get plus minus lambda, right? So here the rate is nothing but plus minus 1, or the slope or the derivative of the penalty term is plus minus 1. It means every time if you update the weights of using the penalty curve using the gradient descent method, okay, it will always update by a constant amount, okay, because derivative itself is constant, plus or minus 1. So here your weights will decrease by a fixed amount every time or on every update. So it will be likely to be 0 at this intersection point because it is getting updated by a fixed amount every time. So your W will keep decreasing and will become 0 eventually. Similarly, if I talk about L2, so in L2 norm, this is again, this is the shape for your penalty, that is summation of W square, and this is again your ellipse contour. Every ellipse belong to a single value of error. Again you will keep expanding ellipse, and till this point here you will meet, and that's where your optimal point is. So the loss belonging to this ellipse will be your final optimum loss, which is satisfying the penalty curve as well. Okay, here the W will not be 0 because here the curve of the penalty is smooth. Okay, and here I can see that the curve, so the derivative of the penalty curve is 2W. So my W is decreasing, and with the W decrement, my slope is also decreasing because slope itself is 2W. So the increment or the change in the W will, with the number of iterations, will also decrease. So W is very less likely to reach 0, or it will not reach 0 because on every update your change in W itself is decreasing. Okay, because change is 2W. W is decreasing and the rate of W is also decreasing. So it will not reach 0. So here it will meet somewhere at non-zero W. Right? So that's why in L1 regularization, the W is likely to be 0. So in the end, one of the weights or few of the weights might be 0. Okay, so the variables having those weights or having those parameters will vanish. Okay, so that's why the L1 penalty or annual L1 regularization sometimes is also used for feature selection. Means some of the features will get vanished at all. Totally it will get vanished and my parameters will reduce, my features will reduce. But in case of L2, parameters weights will reduce. Okay, so the parameter or the variable or the feature will not vanish. Its impact on the output will reduce. That's it. So here you are reducing the impact in L2, and in L1 you are vanishing the feature. So that's why sometimes L1 norm is also used for feature selection, but L2 is used just to reduce the impact of weights, and it will reduce the overfitting as well, because if you reduce the impact of many variables, okay, so it will not overfit the training data, thus the test or the test the result or the accuracy on the test data will increase. So you can imagine, while the ellipse of loss is expanding outward, your weight vector is traveling along the constraint or the penalty boundary during gradient descent. In L2, the smooth circular boundary meets the ellipse gently along the edge. So all weights shrink but stay non-zero. And in L1, the sharp diamond corner pulls the weight path straight on an axis, and that's where one or more weights become zero. Both finally meet at the intersection where the model says, I have reduced loss as much as possible without breaking the simplicity rule or the penalty rule. Now, as we have discussed, how big should that circle or diamond be? That depends on lambda. The large lambda means small constraint, model too restricted, and that is called underfitting. If you have small lambda, large constraint, model is too free, that is called overfitting. So how do we pick it? That is through cross validation. We train the model with multiple lambda values and check validation error. So here is the big picture. Regularization is nothing but the discipline for your model. L2 is smooth shrinkage. It never makes weights zero. L1 is the sparse shrinkage. It makes the weight exactly zero. And lambda is the level of discipline you choose for every penalty. Together, they prevent your model from memorizing data using each and every variable, or it reduces the impact of each and every variable and force it to truly learn the patterns which matter. If this helped you visualize what is actually happening inside the gradient descent and the regularization, drop a comment below, share it with your ML buddies, and subscribe to Concepts of